Okay, part 2 from changing the appearance of radicals. So we talked about simplifying a radical by removing perfect squares from square roots, perfect cubes from cube roots. Now I want to talk about basically a little bit with fractions and radicals. So again, this is going to probably seem sort of arbitrary, and it is at this point in time. It had to do with doing arithmetic without calculators. So if you actually wanted to get a decimal approximation, dividing by a radical was very hard, but starting with a radical and dividing by a whole number was a little easier. So not such a big deal now, but we still need the skill that allows us to remove radicals from the top or the bottom of a fraction. In particular, in calculus, we need to be able to clear them out at the top of fractions. So the idea here is just I don't want to have a root 3 in my denominator. I don't care if there's one in the numerator, but I'm rationalizing denominators is what this is called, rationalize the denominator. And the idea is if I don't want to change the value of this fraction, I have limited number of choices. I can multiply by 1 or add 0. And I don't know that add 0 has come up for us yet, it will. But multiply by 1 definitely helps here. I can multiply the top and bottom of this fraction by the same thing. And if I'm careful about choosing what that thing is, I can make sure that there's no square root left in the bottom. What I would do is say, okay, how do you get rid of square roots? Well, you need squares. Squaring means multiplying something by itself. So if I multiply a root 3 by itself, I'm going to get a root 9. You don't need to write this step once you catch on to what's happening, but just to see it. So you basically have the square root of a 3 squared, or you can think of it as you have the square root of 3, which you're then squaring. Either way, when you square something and square root it, you should get back with just the number that you started with. So I get a root 3 over 3. Do I really like that better than 1 over the square root of 3? No, I don't think it's any better at all. Sometimes I like the 1 over root 3 better. But again, we need the skill that allows us to move radicals to the top or bottom of fractions in this way. Okay, second one, I just wanted to point out that sometimes the root can be simplified, and it might make your life a little easier if you do that first. So let's do it both ways. Let's say, okay, I want to get rid of a square root. I have the square root of 12, so if I get it to be the square root of 12 squared, I'm going to have some luck. So I have a 2 root 12 on the top, and I have a root, here I'm just going to even, it's 144, but I'm just going to write it 12 squared because that's the important thing, the square root of 12 times 12. When you multiply two radicals, you can mush it into one radical, and 2 root 12 kind of is what it is. Oops, 2 root 12. But square root of 12 squared I can definitely do better with. Okay, so fine, but now I have a couple of things to do to simplify. One is I should cancel out a 2. The other is I should say 12 does happen to have a factor that's a perfect square. So I'm going to have a 1 out in front, but then I have a square root of 4 times 3. I have a 6 on the bottom. Square root of 4 is 2. And then yet again, I have to cancel. So I end up with, same thing I had in the last one. I didn't even do that on purpose. Great, nothing wrong with that, right? So it's okay if sometimes you do things a slightly longer way. That's not the end of the world. You're not always supposed to see the very best way right off the bat. That just doesn't happen with math. But if you're watching, I would say, we'll see if my prediction is right, we could say, okay, let's first extract the roots. So 12 is 4 times 3, which means this is 2 over 2 root 3. And I can cancel and get 1 over root 3. A little bit simpler. And now it just turns into the problem I did last time, which is root 3 over root 3 squared, which is root 3 over 3. Okay, so not a huge difference. Might be a little easier if you simplify first. Okay, so hopefully this makes sense for square roots. If you're trying to get rid of a square root, you create a perfect square. You create a perfect square by multiplying something by itself. To extend this to cube roots can actually get a little bit tricky. So if it's not terrible, but we just have to be thoughtful about it. If we're trying to get rid of a cube root, we have to build up a perfect cube. So it's not good enough to just multiply by the cube root of 5 over the cube root of 5. Multiplying something by itself is squaring, and squaring is not going to get rid of cube roots. But cubing does get rid of cube roots. So if we multiply 3 of them, then what we've got is 3 times the cube root of 25, and then on the bottom, 2 times the cube root of 125, but that's the one I want to cancel, so I'm just going to go ahead and kind of shorthand that, say I have the cube root of 5 cubed, cube root and the cube are inverses, they cancel each other out, so I have 2 cube root 25 over 2 times 5. Last rewrite. And again, you can't cancel something out from under the radical. Don't try it, not allowed. So that's as simple as it gets. And that's perfectly fine. Move the radical to the top, you're done. That's the point, is just to be able to move it. Okay, just a couple more for good measure. Again, if you're watching, you can make numbers a little nicer. In this case, I'm looking for perfect cubes, and 40 is 8 times 5. So I can say, well, really this simplifies a little. The cube root of 8 is 2. And then I can actually reduce and say this is 3 over the cube root of 5. And now I can worry about rationalizing. I'm being kind of boring making the same numbers show up, but this will be really similar, right? There's no 2 in it, but if we want to get rid of a cube root, we need a perfect cube. So I'm kind of making a little bit of a shorthand here. So really we need 2 more cube root 5s. So I'm going to have 3 cube root of 25 over cube root of 5 cubed, which is 3 cube root 25 over 5. Okay, so just remember that multiplying by itself is squaring, gets rid of square roots, doesn't get rid of cube roots, doesn't get rid of fourth roots either. So in the fourth root problem, if I want to get rid of a fourth root, I need a perfect fourth power. So really, I need to multiply by the fourth root of 17, top and bottom, 3 more times. I only have 1. So rather than having to write that out 3 more times, I'm just going to say, okay, that's the same thing as this whole thing cubed. Here we can even put them outside. It means the same thing. So we have 9 times the fourth root of 17. I lied. I'm going to put it under the root here because I like it better. Over the fourth root of 17 to the fourth. And the fourth root of 17 to the fourth is 17. I have no idea what 17 cubed is. So again, on a test, if I have monster numbers, I'd either just expect you to leave them or I'd have a calculator. If you're not sure if it counts as a monster number or not, ask me. I will tell you if I think it's something you should be able to figure out. Okay, so we could go through and figure out what 17 cubed is. I feel lazy about it. I'm going to leave it. It's the denominator that I'm really worried about here. So, squares get rid of square roots, cubes get rid of cube roots, fourth powers get rid of fourth roots. That's the goal here. Thanks for watching.